13-2 stuff. We're going to talk about what everybody else in the world does in an algebra 2 class. They talk about things in terms of radians. Radians are the button on your calculator that says rad. It's the ones that give you weird values all the time that you never use. Okay. Where you have your mode where it says radians versus degrees.
I don't see this rad.
Radian measure.
Where's the rad button?
Right there.
Mode. Radian measure is when you talk about degree measure in terms of pi. Okay. So if I'm looking at degree measure, we start here at 0, 90, 180, 270, and 360. Everybody okay with that? When we talk about an angle in what's called standard position, they talk about an angle in standard position. That means one of the sides of the angle is the positive x-axis. It points at 0. The angle, therefore, opens upward. It opens counterclockwise. The angle opens up, and this part is called the terminal side. Be helpful to know what these terms are because you're going to see a lot of it. Okay. So when I say an angle in standard position, that means one side is always at the x-axis, vertex at the origin, one side's on there pointing to the right. Angle is positive, it opens upward, so it's opening counterclockwise to the terminal side. Okay. Now an angle in standard position, obviously positive angles rotate counterclockwise, negative angles go clockwise. This is how these work. What happens here is that we talk about angle measures and what quadrant they lie in when they're in standard position. So if an angle that has a degree measure of 135 degrees, what quadrant would that be in?
1.
2. Remember, this is quadrant 1, 2, 3, 4.
Way harder.
Okay. Bless you. This is where it started. It starts at 0 and it works its way up. Okay. So when you want to place an angle, let's say you had to place 700 degrees. What quadrant would 700 degrees lie in? Well, all you do is you start spinning. Here's 360. Adding another 180 would be 540. If I went to full time around, it'd be at 720, wouldn't it? So it's going to stop before it gets to 720. So what quadrant would 700 degrees be? 4. That's what you're doing. You're spinning yourself around to figure out what quadrant you lie in. Okay? You're adding values as you go through. Okay? If it was negative, you just go the other direction. And that's it.
So we'll always start at 0?
Yes.
Okay.
Yep. That's the whole idea by saying standard position, 0 line, counterclockwise. Okay. Unless it's a negative degree. If I wanted to say where is negative 225, if I want to find out where negative 225 is, I still start at 0, and I just spin around the other way. Okay? So I'm counting backwards.
Sure.
So this would be 0, this would be at negative 180, this would be negative 270, so this would be in the second quadrant, just going the other direction. Okay? That's how a negative angle works. Now they will call it not just an angle, they'll call it theta a lot. So you're going to see a lot of theta. Remember this? You'll see that a lot. Okay. An angle, some theta in the standard position, what quadrant do they lie in? Well, not only do we worry about degree measure, because we start to stay away from degrees, we start to convert everything into what's called a radian. Radian measure is a conversion from degrees to degrees in terms of pi. Okay. What they say as far as a revolution is concerned one full revolution is 360 degrees, or we say it 2 pi. Okay? 2 pi is one full time around the circle. Therefore, what would be at 180 degrees if the full revolution is 2 pi? It'd be 1 pi.
Can we just say pi?
What would be at 90?
Half pi.
Half pi. And what would be at 270? 1.5 pi. But we write it as a mixed, not a mixed number, excuse me, we write it as an improper fraction as 3 pi over 2. Okay, 3/2 pi. All right. Now, in order to convert, we convert from degrees to radians, radians to degrees. To go from degrees to radians is a very, very easy conversion. You take your degree, divide it by 180, and you slap a pi next to it. Okay. So you go the other way,
Pi on it.
go from radians to degrees. You take your radian, you divide it by pi, and then you multiply it by 180. Because what's going to happen here is that eventually we will build into what's called the unit circle. And I think I've mentioned before that the unit circle is really only based off of 3 different angles. Your special right triangles. (30, 45, and 60. So if I take those 3 basic angles, what they do is they populate the rest of this, okay, by being able to convert things back and forth. So let's convert, let me see where I'm at here. Let's convert 30, 60, from degrees to radians. These are the most common ones you're going to use. So you take your 30 over 180 times pi. Simplify the fraction. Zeros drop, and 3 goes into 18 how many times? 6. So 30 degrees is pi over 6. Now, 45 is really easy. 45 was half of 90, wasn't it? What was 90? It was pi over 2. So what's half of pi over 2? Pi over 4. Same deal. And then 60, well, let's do the same deal. 60 over 180. And slap a pi into it. You get pi over 3. Those denominators are going to allow you to figure out what kind of an angle you have each time. And the reason why I'm saying that is because all of the angles that we get into eventually here in the latter half of 13.2 and then the 13.3, if they have a denominator of a 6, it's probably a 30-degree angle bounced into a different quadrant. Because each angle, and we talked about this earlier, if I take this 30-degree angle, it has some specific ordered pair. You guys agree on that? If I move this 30-degree angle into this quadrant here, it comes up 30 degrees off of that. So what's 30 degrees less than 180? 150. So this would be at 150 degrees. The only thing that changes here, the y value is the same. What happens to the x?
It's negative.
It's negative. Now, if I come down this direction, this is 30 degrees more than 180, 210. If I relate it to this, what changes?
Negative x, negative y.
Negative x, negative y, correct. And then if I go over here, it's 30 degrees off of 360, which would be 330. And it would be x and negative y, because it's just vertical from here. Okay? Now, what happens then, if you start thinking here, if this is pi over 6, this is 1 pi. Do you agree? What's 1/6 up from a whole?
What?
What's 1/6 up from a whole? If this is 1 pi, it'd be 5/6, so it'd be 5 pi over 6. Moving down, it's 1/6 more, 7 pi over 6. 1/6 less than 2 of them. If you think in terms of common denominator, to get a 2 with a denominator of 6 would be 12 over 6. Do you agree? What's 1 less than 12? Oops. And that's how these radian measures work. These guys, this 30-degree angle, will have a pi over 6 radian measure. Anything else within that family will also have that over 6. Does that make sense? It'll work the same with the 45s. It'll work the same with the 60s. And we'll start to build this thing out later on. Okay? People start to think that this is the scariest stuff, and it really is easy, because if you know this, you know all. You only need to know a quarter of the circle. You guys like to do this stuff.
Yeah.
All right. We did this, terminal side, draw the angle, blah, blah, blah. We did that. Coterminals, okay. So coterminals. Coterminal angles are the angles that share the same terminal side. Excuse me, I forgot what it was called. So when we talk about the terminal side of an angle, it's where an angle stops. For example, if I have this at 30 degrees, really easy. If this is 30 degrees, if I took another angle and spun it around, it would be 360 plus 30 degrees, which would be 390. So 30 and 390 share the exact same terminal side. It's just spun around them. Okay? You can have coterminal angles that are positive or negative, just depending on the direction. You think of it in terms of a positive coterminal, it was spun around. If I go the other direction, what would that angle be to wind up at 30 degrees again? Is it positive or negative?
Negative.
Negative, because I went the other direction. So, coterminal angles with 30, well, 390 or negative 330, because they're all spinning to end at the same position. So what happens then is that as you start working with all of these different angles, as we look at larger and larger angle values, you're still going to be spinning around into the quadrant, and you're still going to land on the same one of these main values when we start doing the real stuff. Right? Today is more of, can I find a coterminal angle? Can I figure out what position, well, what quadrant does it lie in itself? Excuse me. Did you notice it's just basically adding and subtracting 360? Works the same with radians. Yes, ma'am.
Is there one more angle
Oh yeah.
so it's not just like those?
No, any multiple of 360, really. If I went around, was it 720? So that would be at 750. Add another 722 would be 1470. As long as you wind up, there's infinite coterminal angles at each position, because you can continue to spin around. What we usually worry about is that, can you get one within one revolution? So if you're given like 7 pi over 2, if I'm given 7 pi over 2 and I want to figure out what quadrant does it lie in, it's the idea of finding its coterminal angle that is within one revolution, okay? So now, these are the cases that you think about it without a pi for a second and say, well, 2 goes into 7 how many times? 3, it's 3.5 revolutions. So if I start, I have to go 3.5 revolutions. So here's 1 pi, 2 pi, 3 pi, and a half. I end there. So what was that angle as far as within one revolution? It was 3 pi over 2. Okay? That's what that means. You're able to spin it to figure out where is it within one revolution. That's the importance of learning how to work with coterminals. Okay. I think I might have lost something on that.
I think we got it.
Yeah, you're trying to figure out where does it lie in terms of one revolution. Okay? Because any angle can be spun to you find a coterminal angle that lies within 0 to 2 pi. No matter how large it is or how or negative it is, you can backtrack it to be within the one revolution so that you can find what's called a coterminal angle. Because eventually, this is a functional angle that I can work with. This is not. Okay. Here I can find sine, cosine, tangent, cosecant, secant, cotangent value, whereas here it's a lot more difficult to use. I'm trying to make it within the one revolution so I can work off the ordered pairs. All right. Let me try again. Is it the pi one that's weird because you're not used to pi yet, or do you want
Yes.
to? Okay.
Yeah.
Let's look at. We'll try a couple and then degree. 600 degrees. I want to spin it to win it. That was a bad joke. A little bit. Again, what we're gonna do is we're gonna figure out what quadrant does it lie in, so that we can figure out what would be its coterminal angle. That's 360. So I'm backing out the 360. I have how much left to go? Well, I have 240 more degrees to go. Okay. If I continue, here's another 180. How many more do I have to go? 60. I have 60 more degrees to go, which means I'm a little bit past halfway. And see how I was stopping at the quadrant, or at the 180s and the 360? Because now I'm asking, well, how much further did I have to go down? I had to go down another 60 degrees. So what was 60 degrees more than 180? Bless you. 240. We already had that there. So this is 240 degrees as its coterminal angle. At 240, I know that it was below the x-axis by 60 degrees, which means it'll eventually, when we start talking about these, have what's called a reference angle of 60 degrees. Just like these guys mirrored themselves across the quadrants, a 60-degree angle mirrors itself across the quadrants, and its value, those ordered pairs just change signs, S-I-G-N. They change signs as they go around. So the whole idea of placing them into the correct quadrant will allow you to find these ordered pairs to bounce through. Yes, ma'am?
So you're just trying to figure out where or find whatever.
Working with coterminal angles is getting you to be able to find what's called a reference angle. Reference angles are going to be your specials. A lot of times today, a lot of the exercises are going to be what's a positive and what's a negative coterminal angle for this. you're just gonna spin it to figure out where does it lie within 360 degrees, and then you backtrack it, where would it have been as a negative angle. So if I went, again, if I go this way, if I go that way, well, that's where some of the negative stuff can be a little bit weird. We know that one revolution, excuse me, that it started at the 240. If I come this way, what would it be? How you do? You subtract another 360 off of it to get the negative. It'd be negative 120 of it. What happens with these angles, when you start with a larger angle that's outside of a revolution, what I mean by revolution, one full circle, 360, you subtract it until you get your last positive value, and that means that's you're within one revolution. You subtract 360 one more time, and then there's your negative angle. So if you start at 900 degrees, if I start at 900 degrees, all I'm going to do is take 900 minus 360 minus 360. I'm at 180, okay? I know if I subtract 360 again, I'll be negative. So 900 degrees, 360. Oop, I went too far. Yeah, 720, and it's going to wind up here.
Seriously, how is that possible to scale?
I don't know.
That's fast. They can just go pretty fast.
It's called angular velocity. Angular, that's great. Angular speed, angular velocity.
Yeah.
So you wind up at 180 degrees. That's within one revolution. If I go the other direction, that would have been at negative 180.
Oh. Okay.
What happens here is that you're adding and subtracting. You'll add or subtract values of 360. Now, if you start within one revolution, if I start at 150, that's already within one revolution, which means I need to find more and the negative. Yes, ma'am?
So basically, for like, if you have a big number that's more than one revolution, you just keep subtracting 360 to
Yep. That's all it is. Okay. Here, what quadrant does that lie in?
Is that
2, yeah. It lies in the second quadrant. Okay. How far is it from 180 degrees? 30. So it's 30 degrees above 180.
Yes.
So I know that the negative one would be negative 180 minus another 30 would be at negative 210. The positive coterminal would be taking this and then continuing around one more time. So you're adding 360 to it. So it would have been, would have been at what, 410? Yeah, excuse me, yeah, thank you, 510. So if you're already starting within one revolution, you add 360 to the value, and you subtract 360 from the value. That gives you your positive and your negative coterminal. It's usually the ones that are over revolution that people freak out on. And that's why I did more of those. Okay. Now, when you deal with pi, it's the same basic principle. But I think we'll stop there and worry about pi stuff. Melms, I need your book. Hey, I saw you're going to state.
Yeah.
Congratulations, kid.
I won't be here Friday.
All right, neither will I. Sweet.
So when's Monday?
Now we also.
Well, I'm staying in your city.
Is that now we agreed on?
Yeah, we agreed Monday. Monday, there's tomorrow.
I'm not studying Thursdays.
I'm not gonna be here. Maybe Thursday. After class will be here Friday, so we might try.
Well, that last that's what Libby's
Yeah. Stay.
So on these problems, they're mixed in between degrees and radians. Radians are the ones with pi in it. So there's a mixture of radian and degree problems. It actually goes through 51, sorry. All I want you guys to do is the degrees. So let's see, 1, 2, 3, 7, 15. Okay. There's only 15 of them.
So the ones with pi, we don't do.
Yeah, if it has a pi in it, don't worry about it, because what you're going to do is you're going to draw an angle. So you're going to put it on the axis, spin it to what quadrant it goes into. Find a coterminal, positives and negatives. And then convert from radians to degrees.
I can do that.
Okay? So you're going to go from degrees to radians, so all you're doing is dividing by 180 and slapping a pi next to it. Try to do it without a calculator. You're going to need to do it without a calculator. Okay? And we'll continue with this. I don't know if everybody heard me when I said when we do the quiz jump, I will make sure that your ambiguous case is not going to bounce out of law of cosines. It will bounce out of the law of sine. You don't have to worry about ambiguous or cosine. Are they over there? Oh, they are.